Hi, this is Professor Snell. I want to review heat loss. Uh, we covered this last semester, but we need to understand peak heat loss in order to uh, roughly size our HVAC systems, which is part of what we're doing this semester. So, as a reminder, last semester, especially in my section, I think that Professor Thomas was preparing for this semester, so we talked more about peak heat loss. I talked about uh, total heat loss and gain, and the reason why was because we were designing passive systems for a single, small building using the site resource, sun and wind, and also designing an envelope that was appropriate for a given climate. And so, as part of the envelope design, we need to talk about, well, actually, as part of the complete building design, we have to talk about how much energy the building is going to use. And we can simulate that in Climate Studio, which we did in that thermal analysis simulation at the end of the semester. We talk in terms of site EUI. EUI is energy use intensity. We have a baseline that's for typical buildings. Just think of a code building. For this type of building, this was a residential that would have different baseline EUIs than an office building. So we define that first. And then we sort of in a game, try to get our site EUI well below the baseline EUI because this is just a pretty lame number. We need to do much better than that. Uh, and so we get energy use intensity outputs. So, for example, this chart is telling us the kilobTUs per square foot of loss. So this is meaning that we could compare any type of building per square foot and see how they compared. And we can look at different for example, here we see there's, by the way, this is in New York City. We still see that our configuration right now has still a fair amount of heating load, but no cooling load. And hot water, we didn't talk about last semester, and lighting, we didn't really talk about. We could also look at the energy use, not per square foot, so it would be on pure, so if we had a small house, of course, it's going to use much less energy than a huge building, but it might use more per square foot. And then the most interesting chart to me was this energy flows chart where we can get a breakdown. So, for example, here we see the windows in orange. We're getting good gain in the winter, which is great because this is a heating climate. We know that we just saw that we had heating load. So that actually those windows are decreasing that for us. So that's great. But in the summer, we see we're still getting some heat gain, and we wouldn't want that because we're cooling at this time. So we could try to shade the windows or do something to reduce this, though we don't really need to since we don't have a cooling load anyway. So that's the way we were using this, and it made a lot of sense. And then we could talk about the envelope, etc. It made a lot of sense in terms of what we were doing. There's another concept that we touched on, and there was an assignment that I really didn't. I morphed into something different in my section. And so I want to review that and also give people who were in my section last semester tools to that they may not have gotten. So let's talk about peak heat loss. First of all, we talked a lot about basic climate variables. And one thing that we discussed was design temperature. So we have a design temperature for heating and cooling. That basically is, you see it's 0.04% in this case for heating and 99.6% for cooling. That's just basically saying we're going to pick a temperature. We're going to look at the climate data, pick a temperature that below it for heating, we don't care. We're not going to design our HVAC system to deal with that, and we'll have some little, we might have a little bit of electric resistance heating or something, or just say we're going to put a sweater on for the 4 hours a year that's below this temperature. We're not going to worry about it. That's design temperature, and there's different percentages we would use. 1% is common, so anything we pick the temperature that there's 1% of the hours that are below it. Anyway, that's design temperature. And heating degree days and cooling degree days are central to this because that's telling us when we're heating and cooling. But when we get into peak loss, we're talking about how much energy we're losing when the building is in the worst case scenario, when it's either the coldest or the hottest outside. So here's a spreadsheet I made. that's related to this. So I'm going to talk a little bit about spreadsheets in case you haven't used them very much, because they're a good thing to get into. This looks maybe daunting right now, but I'm giving it to you in Canvas so you have it. And once I've explained a little bit about it, I think first of all, you can use it for your assignment too. And secondly, it's a good way to, first of all, get involved in Excel, and seeing the power of Excel on a very basic level. And also, it's a good summary of if once you sort of understand how this works, it's maybe a good resource. And thirdly, it's also going to just remind us that this is really a way oversimplified. Even this is pretty complicated, it looks, but it's so oversimplified that the reason I really didn't cover this last semester is this is not the way we would really do it, because we would either use a canned like a manual J, which is a preset template for how mechanical engineers quickly determine sizing of HVAC. We would use something like that, or we would do something in a simulation, because it's pretty complicated when you actually get into the details of this. Okay, anyway, let's just talk about Excel for a second. Um, Excel is basically a calculator, or that's one thing you can do with it. So you can put numbers in and then apply equations to them. We can also generate charts from Excel very easily, and it's a great place. You can link to different cells across sheets. So like here, I have a small sheet and a big sheet, and I mean it's a sheet called just named small, one named big. That's for the size of the building. Um, and we could link across different files. So it's incredibly powerful. Everything that you use that behind, like the simulations we're doing behind them are, very complex spreadsheets like this. So it's good just to get a basic understanding of how it works. What I've got here is I've got a key on the left, so pretty much anything that I use as a symbol over here is described and I'm actually going to go in here and I'm going to color this because I think this is the most important one. The most Q is the main thing that's peak heat loss, and that's these yellow um, cells are our Q values, which is you can see here. Um, so I've defined all my terms on this side, and in order to make my spreadsheet more compact, then I'm using symbols. Like so, for example, um, this is the thermal bridge loss, and where's my symbol here for that? So it's called psi value. That's the symbol. It's BTUs per hour per square foot degree Fahrenheit. I'll talk about that in a second. Okay, so peak heat loss or heat loss in general in a building is the result of um, losses, right? And we have transmission losses through opaque envelope surfaces. So we have floor, walls, and roof. Of course, this could get very complicated because we could have a bunch of different walls. We could have a bunch of different types of floors and roofs. I've simplified it here, just have one for each. Um, so these are the opaque assemblies that we're losing heat through. We also lose heat through fenestration, which in this case I'm meaning to be windows and doors that are glazed, that have glass in them. And we have a variety of variables that determine the heat loss for them. And then we have infiltration, which is leakage through holes in the envelope. Those three things together create our total heat loss, our total Q. And Q here means peak heat loss. In other words, it's the heat loss when the building is either at the hottest or the coldest. It's the worst case scenario. And so you need to design an HVAC system for that worst case, right? You need to be able to produce enough heat or cooling when it's the coldest or hottest. But that's where we have a design temperature. So over here here's our little program. Um, we're going to have a design temperature I'll talk about and a building geometry. If you input these values, and by the way, in this spreadsheet, anything in blue is something you can change. Anything in green is going to be a sum of, or it's going to be a formula, and the yellows are also formulas that are the Q values. the peak heat loss value. That's how I've organized this. Before we get into the program, let's just talk about Excel a little bit. Um, to make things, let's say, let me click on R total, and I come up here, and this is the formula that is represented by R total. I've got 1 divided by J21. If I click on this little formula dialog, then it will highlight the cells that are in the formula. So here's J21, 1 divided by J21. If we have a U value, if we 1 divided by that U value is the R value, the reciprocal. That's what that equation is. Here's another one. What is this? J21 times H23 times big exclamation point delta T. So let me select that. So H21 is the surface area of this raised floor. H23 is the U value, and big delta T is the change in temperature. It's right here. For our design in our climate. And why does it say big exclamation point? Because that's the sheet we're on. So I've made a constant in that cell. So in other words, if I were to type in delta T on this page, it's going to in a formula, it will reference this cell. Now, okay, I've already lost you if you don't know Excel. I'm just trying to give you some basic idea of how to start looking at this if you want to learn about Excel. You don't need to know that in order to use this spreadsheet. Um, okay, so that's the basic idea. How is this, or how Excel works in a very, very simple way? How is this spreadsheet set up? We have the program over here, and that is our design temperature. So we're in New York City. I decided that my design temperature, in other words, that thing we were looking at in the other spreadsheet, I'm not even saying if it's a 1% or 0.4% or whatever, or 0.04%. I'm just saying that we're designing for 15 degrees Fahrenheit. Anything below that, we're not going to worry about. And then our set point, which means the temperature we want it to be inside, is 65 degrees. So the delta T, which again, here's a little formula, 88 minus, so it's 65 minus 15 is the delta T, is 50. So that's going to be the delta T we're using for our heat loss calculations. Lots of things have the change in temperature in them. Then we have our building geometry. Very simple. I just did width of the building, length, and height, so we can get a surface area of the envelope. And then I've created areas down here in volume and an area to volume ratio. Because, well, we won't even talk about that. That's something we could, if anybody wants to ask me a question about it, we can, I'll bring it up and make him up later. Um, so then what did I do? I have in my losses section, I have transmission losses through, like I said, assemblies, opaque assemblies. And all I've done here is I'm describing the layers. So let's go over here to the walls. I've got drywall, mineral wool insulation, cellulose, wood stud, plywood, mineral wool, wood shakes. Now, I probably should have, well, it'd be easier if I showed you actually, I'm going to do that. I'm going to pause this video right now. Okay, here's the basic envelope that I put to the spreadsheet. We've got a wood stick frame with framing for the floor and roof. And then there's just a bunch of not miscellaneous, but layers that, oops, actually I don't need, which is one. A bunch of layers, control layers, but the ones that are going to be dealing with heat are thermal. So I've got insulation in the wall cavity. I've got insulation, of course, in the floor and the roof. I've got an interior furring insulation, so there's furring strips in there, and exterior insulation in this air gap. And then there's a bunch of air and water vapor layers, and where's my finish? And then some shakes. So this is the building system that I'm describing in very simply the wall system. So we had drywall, we had that mineral wool was on the interior. There was a furring cavity in there. Then there was cellulose in the so drywall, mineral wool. This is from the inside out. Cellulose in the stud cavity, wood studs, plywood, mineral wool, and then shakes. Those are all have resistance to heat flow. Um, this is their thickness, and this is their R value per inch. Then there's two paths here, right? Because um, the wood stud, uh, when there's a wood stud, there is no cellulose, right? So we have to then basically, we have everything's the same in this path, except for where in path one we have cellulose, and in path two we have the wood stud. Okay, there's an interior and exterior air film that we should have. You should know what that is. It's just basically there's a resistance to heat flow in the interior and exterior because of the air that's basically the surface tension of the air. Um, okay, so then we have. I pause for a second because I'm hoping there's nothing wrong with my microphone because it seems to be buzzing in my ear a little bit here. Anyway, so we have all these R values and we totaled them up for each path. Then we need U values for this calculation, so I divided by 1. Then 90% of the path, 90% of the wall is path 1 with the cellulose. If you think about it, there's just a small percentage that's wood, and you can calculate how much that is. In other words, if I go back to this, let's just look at that because I want to be super clear. Um, if I take off some of these, let me turn off all of these. So, in my cavity here, I've got 90% of this, the surface area of this wall is going to be the cellulose insulation, 10% is going to be these studs. That's the idea. Okay, so back to this, and then we were here, and that's where we got the 90 and the 10%. And so then we get total U values based on the percentage of each of these paths, and then we add them together, and we get a U value total. I went ahead and did an R value because I like seeing that because I think in R value more than U value. But the point is, um, if we calculate the square footage of that, the surface area of that wall, and with all this information, we can get a peak heat loss because we're now using the delta T. We're saying the surface area times the U value times the delta T, which is the 50. We get a Q value, which is in BTUs per hour. Now, if you do that for your floor and you do it for your roof, um, then you can add those together, and we're on our way. We've got that. We've got the losses for the opaque systems. There's also, if we have a slab on grade, there's a way that we do this differently, and this is again a total estimation. So I didn't do a slab on grade because I have, in this case, have a frame floor. So we don't have a slab on grade. But if I did have a slab on grade, then I could use this really basic. There's these constants that are based on how much insulation you have underneath the slab or on the outside perimeter of the slab. So you use a perimeter. So if I put in 100, I don't even know what the perimeter is. I can get a Q value here, right? And that would add into these. I'm not going to do that. Just letting you know that's why that's there, and you could use that if that's the case for your building. Um, and again, simple. There's this thing called the F value, which is heat loss factor. It's just a coefficient. There's 3 of them that usually are listed in books. I think this is the lowest. Um, and again, they just if you when a building's sitting on the ground, it's losing heat through the ground, but that's a different environment, so there's a different way to calculate it. Again, this is really kind of old school way of doing it. Um, you do a perimeter of the entire building. You apply this heat loss factor, and you get a Q value. Okay, so that's for our, now we've got the transmission losses for the opaque walls and for the slab if we wanted it. Then we come in and we do our fenestration. So what's going on here? Well, I've got a solar heat gain coefficient that I'm assigning to each unit, each set of windows on the north, east, south, and west, because I might actually want a different solar heat gain coefficient. SHGC means the percentage of heat hitting that glass that's going to go through the glass. So zero point 0.4 is pretty low. If I really wanted to get solar gain in this building, I could find some glass that had like a zero point 0.7 probably. But that's what that is. It's just a number that we can change. So if I change it, it changes my total fenestration heat loss, and it will change my um, the value that's going to go into the heat loss for the building. Um, there's other stuff in here because we need heating degree days and the total heating degree hours per and heating degree hours or kill heating degree hours are heating degree days times 24 divided by 1,000. It's just a way of getting hours from heating degree days. Anyway, don't want to confuse you. You don't even need to deal with that if you're using this calculator. But what we're saying is that we've got a certain amount of heat coming through the glass. This SIRF is a solar irradiation reduction factor. It takes into consideration, let's just look at it. Reduction factor that considers shading, dirt, and glazing fraction. So, in other words, if we have mullions in the window, that's going to cover some of the glazing. So we have to reduce things. If there's going to be dirt on the window and any kind of shading, we can put that into this. Then we have the area and the U value per unit. That's based on what we choose. And then we have the global horizontal irradiance, which is how much sun is hitting our window. And then we have total heat loss and then solar gain because we have loss through the glass, but we're also gaining it with the sun coming in. And then we get a total fenestration heating season load because we're talking about right now this delta 50 is for the heating season. Okay, but the point is we put all those things together. You can go through these calculations here by looking at them in Excel because I'm supplying this to you and you can figure out exactly how we got to this. But we're saying that all of our floors are 15,000 BTUs per hour. Our walls are 23,000 and our roof is 9,000 and our windows are 50,000. So a lot more through the windows makes sense because they're not as insulative, right? Okay. Now we also have heat loss through infiltration. Keep kind of adjusting things here. All right. Briefly going over this. So think about it. The surface area of your building is where heat is going to move through. It's going to be lost. So we have cubic feet per minute at 50. That's 50 pascals. So we need to define a pressure that this is happening at. So we're saying that we have a building sitting there. If we pressurize it, in other words, we change the pressure so there's air pushing into or the inside or the outside of the building. Um, we define that per square foot. So this is 0.06 CFM 50 per square foot. Now, why? This is a high performance building setting. You could look up different ones or just leave this one. It's basically we're saying how we're designing the building to perform. We're saying we want this building to only lose 0.06 cubic feet per minute of air at 50 pascals per square foot. Then we calculated the air exchanges per hour. That's just basically taking the total CFM, which CFM is then cubic feet per minute. Then if it's per square foot, then we need to know how many square foot there are. In surface area, we can get the full square footage. We can use that to get an air exchanges per hour, which is the way sometimes this is done. In other words, you need the volume then. If you know how much air your envelope is leaking, then if we know the volume of the building, we can figure. So this is per minute, so we got to change it to hours and bring in the volume. You can look at how that works, and we've got an air changes per hour. Whatever, doesn't matter. Then this also takes into consideration. I mean, it matters, but I'm saying you don't need to understand it to use this tool. We have how efficient our energy recovery ventilation is. We'll talk about that later in the semester. We have losses from ventilation, and there's also a you adjust this based on the climate or the situation, and the whole thing is based on a how much the density of the air, because that tells you how much if you have this much if you have 0.06 CFM at 50 per square foot, and all these other losses, you need to know how much heat is moving through that air. All those together, here's the equation for it. We get a heat loss through air infiltration. So what do we have then? We've got design temperature, building geometry, design temperature here, building geometry here that we input for our design. We have wall, floor, wall, and roof designs that we put in so that we can calculate their U values and come up with a heat loss for each of them. We do the same thing for fenestration. There's a series of variables we need to adjust, and we get a heat loss for it. Then all these show up as totals in our peak heat loss, and we get a total peak heat loss. This is the number that we are designing our HVAC system to deliver. This is how many BTUs of heat we need to deliver on the coldest moment of the year. Then I went ahead and just calculated the total heat loss in that this is all in the heating season only. So this is in heat loss in kilobTUs per year, and we have that there just as an extra thing. Okay. The point here is that you can come in and set your design temperature, your set point, put in the parameter, the basic length, width, and height of your building, define your different wall and floor systems. So for example, in the assignment that you're going to have to do, you need to do this for individual rooms, maybe you won't. But you could then just run this for each room separately and add them together. And you need to know something about your windows, and you can so you use these as individual calculators for different things, then just write the number down or put it in a different cell down here, and then do a calculation off of it. The one thing I did not talk about was this little section here, thermal bridging. We did talk in class about how, for example, if we go back to this model, oops, wrong thing. If I didn't have insulation on the outside of these, let me just turn off a lot of this stuff. I'll just turn off all of this. And I'll turn on all the, oops, can't do that, okay. If I just had, this is a typical insulation scenario where you have studs and you have cellulose or some kind of insulation between the studs. Now this stud becomes what's called a thermal bridge because it's breaking the insulation. It has less R value, less resistance to heat flow than the insulation. So it is now degrading we can't say that our building, well, it's degrading the insulation value of our insulation material by breaking it. In the case that we just did, we just said, okay, we're going to make this 10%, this 90%, and we're just going to add up the paths for each of those zones. That can work, but it only really works for sure if you have insulation on the outside. So again, this insulation on the outside of our cavity allows us not to think of that cavity as a thermal bridge or those studs as a thermal bridge. If this is much worse with metal studs. Metal studs are really they suck heat through them, so they really degrade the insulation value. So if we're going to be really accurate, or we don't have insulation covering the outside, we need to calculate what's called our thermal bridge psi value, which is just the total amount of heat we're losing through those bridges. There's a way of doing that by hand. It's usually done there's a program called Therm that a lot of people use, where you bring in a drawing and you apply the different materials to the drawing, and it calculates it itself. All I'm doing here is making the point that this value here or here is not accurate, and that we actually need to do a thermal analysis, a thermal bridging analysis. I just made the simple. Sometimes you just, if your thermal bridge is small enough, then you don't need to consider it, and so you calculate it just to see if you need to consider it. The best thing to do in design, by the way, is just not to have thermal bridges by having insulation unbroken around the exterior of your building. So you don't need to change these, and they're not actually, you can change them and play with them if you want to learn about it, but it's just here to show you that there's another set of calculations that are required. It's not as simple as this, and that this is just for the peak heating, and there's so much more that goes into it. So this is not the way you would probably really do it, but this could work as a very basic initial calculation if you were designing a house or something. Okay, that's all that I wanted to introduce with this. I'm going to share this file on Canvas, and I'm actually going to, well, I guess I can just say to the people who are in my class who are now in Professor Thomas's class that might be watching this, if you don't have this spreadsheet and you would like it, just email me. You have my email from last year, and you can, and I'll send it to you. All right, I hope this helped, and I'll talk to you soon.